In this set of notes, we're going to begin, as usual, with a quick review of what was covered in the last set of notes, and then we're going to move on forward to the main topic for this set. Last time, what we had been looking at in quite a bit of depth, actually, were rules for how we can draw good field line diagrams. So I want to review those rules with you briefly. Then what I want to do is move on and continue our discussion of how we can understand the physical behavior of conductors by looking at how field lines behave near those conductors, in particular following these set of rules and an additional set that comes about when we begin to contemplate the physics of conductors. So we'll be reviewing first our previous discussion of a solid conducting cylindrical shell, which had been charged with a charge negative lambda. A line of charge plus 2 lambda was sent down the center of that particular cylinder, and we had analyzed how the charges would then redistribute. What I want to do today then is to draw a general set of rules regarding field lines and conductors from the specific lessons that we had learned in that example. So, just reviewing briefly the main points from the field line rules that we had learned in the last set of notes, and just to kind of firm them up in our minds, there were a set of 5 rules, basically, that things boil down to. The first one is this rule regarding line density. The number of electric field lines per unit area we saw was directly mathematically proportional to the strength of the electric field at any location. That concentration of lines with high density in regions of large electric field was something that we were able to understand directly by the mechanical fluid analogy. That kind of shows you the power of this thing. To prove that mathematically in the electric field case can get a little bit complicated and it can feel a little bit abstract. But we all understand this idea, I believe, that when you are near, for instance, a running stream, you're going to where the stream is shallower, where all the field lines have to concentrate, where you have to pump a large amount of fluid in a small amount of space, the velocity has to go up. Very similarly, when you are concentrating a large number of field lines, electric field lines in a given area, you're going to find that's where the electric field is the strongest. The second rule is somewhat related to this first rule, actually. What it tells you is that the field lines, they always begin or end at either a positive or negative charge, respectively. That again comes about from our fluid analogy. Remember how the fluid analogy works. In the fluid analogy, right, the way we represent a positive charge is by a source of fluid, right? One of these balls that injects fluid into the system. Well, if we have one of those positive source balls, clearly then, if we follow the tracer particles in the fluid, they're going to be originating at that positive source, right, and then moving out into the fluid, either outward towards infinity or perhaps ending then somewhere. But where they end is somewhere where they must be absorbed. And that is how we represent actually negative charges in the fluid analogy. So wherever we see a field line ending, we know then there has to be a negative charge. And where a field line begins, where we're injecting the fluid, that's where we would have the positive charge. The next set of rules, again, is very closely tied to that analogy. That has to do with the number of field lines we have, which represent the amount of fluid, basically, that are leaving or entering a given charge, depending on if it's negative or positive. But the number of lines should be proportional to the amount of fluid in the associated analogy, or in the case of the electric field, that would be proportional to the charge. When we draw diagrams, a typical convenient number, it's up to you. This is just a proportion for these diagrams. A very convenient number typically is around 8 for a given charge. But if you have a problem where you've got a charge Q and another charge 1/2 of Q, drawing 16 lines might be a lot. So you might choose 8 lines for the Q and then only 4 lines for the half Q. Okay. Next, we have the fourth rule, which is actually very closely related and really kind of a consequence of the second and third rules, which is namely that lines can't begin or end without a charge. We just make this a separate rule, actually, because Sometimes we lose track of this in constructing a diagram, but really what it's saying is, well, if the charge began or end, we know from Rule 2 that means there must be a positive or a negative charge there. And also we know we can't just begin or end or enter or leave a region, right, without there being a charge Q there proportional to the number of lines that are being created or which are ending. So just always keep in mind, you can't have your lines just stop somewhere. You either have to indicate that they're going off to infinity or indicate some little plus or minus on their ends just to alert the grader, say, that you are aware that there must be a positive or negative charge at the beginning or end of that line. The final rule helps us resolve sometimes some conundrums that come up in more complicated cases. You always have to keep in mind that your field lines can't cross. Again, this is a very intuitive consequence of the mechanical fluid analogy. In an incompressible fluid, you can't have two chunks of fluid simply pass right through each other. Similarly, the electric field lines, when you draw a diagram, you can't allow them to cross. That tells you then lines that might want to cross are going to have to kind of sort of merge parallel to each other. You will see when you begin to practice this. But the main point, I think, is to keep in mind that fluid analogy. It'll keep things clear for you, how things are flowing, and you won't run into this rule too much. But you want to be aware of it to make sure your diagrams are accurate. Okay, so that was a quick review of what we had learned regarding field lines and our 5 field line rules. Now I want to move ahead and review briefly and call to mind what we had concluded about looking at this first example of a conductor. But remember, this isn't just idle review. We want to draw certain lessons out of this that we are going to use later as we develop a special set of rules to deal with what happens to field lines, particularly when they are near a conductor. So let's look at what that example really entailed. So I've redrawn our conclusions from that example for you here. So again, basically what we had was this solid cylindrical shell. And on it we had placed a charge minus lambda. And down along its axis we had placed a long line of charge. This is all imagined to be infinite and very long, a nice simple cylindrical geometry. And the line running down the middle, we had on it placed a charge of 2 lambda, lambda being charge per unit length measured in coulombs per meter. So down below here, I'm showing you an edge-on view of what this would look like. If you look straight on, that makes it a little easier to draw the diagrams rather than try to draw them in a full 3 dimensions. And here on the left, I'm showing you our guess at what might happen before we really included the physics of the conductor very closely. Our initial guess was that, well, we have this plus 2 lambda. It's a little hard to see here in the diagram. On that dot representing the central line, right? That was a charge we had placed there. And then on the conducting shell, represented by these 2 concentric circles that I've hashed in here, we have placed a charge minus lambda. A good initial first guess, maybe a little bit naive, but a good first guess, of course, would be that, well, all the negative charges that we've placed on our conductor would, of course, be attracted towards the center. So we imagine maybe placing minus lambda charges onto the inner surface. Now, following our rules, we know that with this positive 2 lambda charge in the center, we would have a set of field lines traveling outwards, and I've decided to represent 2 lambda by a number of field lines equal to 8. What that means then is that the negative charges, which add up to minus lambda, which have concentrated onto this inner surface, are going to have just enough, if you will, sucking power, right, to suck up 4 field lines, because the number of lines beginning or ending have to be proportional to your charge. We had twice as much charge in the center, represented by 8 lines, so 4 lines would terminate then on this inner surface, and I've indicated that with these 4 minus signs and the diagonal lines happening to terminate. You could do it either way. I just thought this would make a nice diagram. You could terminate either the diagonals or the 4 compass directions. It's kind of up to you, but I thought this would work out kind of nicely. So that was our initial guess as to how the charges might distribute. Those minus charges there, they stop 4 of the field lines. The other 4 field lines, of course, then would be free to move off out towards infinity. Now, this is where we began to consider the physics of the conductor in a little bit more specific depth. When we began to think about the physics of that conductor, we realized, well, there's a little bit of an issue over here in this region where we have electric field lines inside of our conductor. Remember, that means, because we have some concentration of field lines here, that there is in fact a non-zero electric field. And as we've discussed in our polarization example, when you have a non-zero electric field, that means that any charges that are free to move, either negative or positive, and recall, you can view it either way, as negative or positive as the mobile charges. The point is, it's a conductor, so there are mobile charges, and as soon as they feel this electric field, then by the basic force law that F equals QE, we know then instantly there will be a force on these. If we think of the negative charge carriers, for instance, they will feel a force in the opposite direction from the electric field, so they would feel a force inwards. And so negative charges in this region of the conductor would begin to move inwards towards this inner surface. So we know then that we are going to get some additional polarization on the inner surface, and we will collect minus charges on there until we have just enough negative charges in here, right, to finally cancel out that electric field. We know that the electric field has to get to the point where it's canceled out, because if it's not canceled out and we still have some field lines penetrating, we know there will be continued driving of those negative charges inward. So we can imagine, if we focus on the fate of this field line here, that some negative charges that might have been mobile and in the interior there, we're going to move inwards and end up on the edge there of the surface, right? And then what that is going to do would be to put enough charge, and that's going to continue. I've got enough charge there to basically eliminate that field line. So let me kind of try to cross that out there. That field line then would be gone because that negative charge had moved his way inwards towards the inner surface. Now, a similar thing, of course, is going to happen to all of these other field lines, which eventually brings us to the diagram here on the right, where I finally brought in enough negative charges so that all four of these original penetrating field lines now are stopped at the inner surface, because we can have no electric field in the interior, like so. Next, we're left to ponder, okay, what happens to the corresponding positive charges? You might, for instance, think that these negative charges are all going to come from some location maybe in the middle of the conductor. So maybe I've left some positive charge here right inside the interior of the conductor. If that were the final situation, I again have somewhat of a conundrum. I would have a serious problem here. The issue is that, remember our field line rules, if I ever have an uncompensated charge, meaning a positive charge that doesn't have negative charges right around it to cancel it out, just a free-sitting positive charge, it has to be a source of field lines. So that would tell me immediately there are going to be electric field lines coming outward from this positive charge. But that would indicate, oh no, now I've got an electric field again inside my conductor. And we know conductors will not tolerate that. That will cause motion of charges that will do whatever they can to cancel this thing out. So those the plus charge that might have been left over by this minus charge coming to the surface, he can't be here inside the conductor because he's going to generate these field lines, and as soon as he generates field lines, new negative charges from inside the conductor, say little guys over here, are going to move towards that positive charge until that whole situation in there gets canceled out. So that's why in the diagram here on the right, we were able to conclude that, well, in fact, the positive charges that represent the additional negatives that collected on this inner surface can only be existing on the outside surface of the conductor. If they were inside the conductor, they would generate field lines inside the conductor. When they're on the outside, their field lines at least can escape so that we have no field lines there inside that conductor. And if you think again about the process that was happening, when I brought that minus charge to the interior surface, he must have left one positive charge somewhere, so I could indicate that here on this at this outer point, as I did here on this diagram. And so basically each of these field lines will turn into a minus pair and a minus plus pair, with the minus left on the interior surface and the plus left on the outer surface. Finally, those last four charges lead to field lines that then can continue to infinity, right, where there won't be anything left to stop them. And we have our final field line pattern as a last final cross-check on the whole situation. We can check the total charge on the conductor. There's now minus 2 lambda gathered on the inner surface, precisely enough to cancel out the interior plus 2 lambda on the inner line. We then have concluded that there were 4 positive charges on the outer surface. In our diagram, those 4 charges by our convention corresponds to a charge of plus lambda extant on the very outer surface. And then if we look at the final total charge on the conductor, it's minus 2 lambda on the inner surface plus lambda on the outer surface, which sums then to a negative lambda. So that, which is exactly the charge that we had placed on the conductor in the first place. So we have now a coherent view of what process occurs when I expose this conductor to this particular arrangement of charges. And you'll notice some very interesting lessons are starting to come out in terms of what happens with field lines and how charges distribute on the outside of the conductor. So what I want to do now is to lay out a set of field line rules that will describe the physics of conductors in an electric field situation.